Hello students. This second part of this wave optics is diffraction. I call it as a diffraction. Some people call it as a diffraction. It doesn't matter. The meaning is same. It means the light bending around the surface of the obstacle. When the light is coming close to any obstacles like opaque objects, it bends along the surface. That property is called as a diffraction. If you keep a ball, opaque transparent. Transparent means light can pass through it, opaque means light cannot pass through it. Translucent means some light can pass, little amount of light can pass. If you take the paper with oil soaked, that is a semi-transparent, it's called as a translucent. And if you take one ball or one cardboard, keep it in the path of the light rays, and here is the screen or wall. Light wherever falls, no, that brightness you will notice. But this much is the size of the object, same amount of light should not fall here. Wherever light is not there, that is called as a shadow. Shadow is the place where there is no light. So if you stand here, shadow is falling means light is coming here and obstructed at this place. But if you have the light source from different directions, no, it's possible to have the multiple shadows. Or the light is coming from the sideways, then shadow may not be there. Or due to the diffraction also, shadow may not be there. What is that relation? Is here, the light should fall up to this, light should go up to here, light should go. If light is really traveling like a straight line path, according to ray optics, light travels in a straight line path. But here we are discussing the wave optics. Wave property, one of the properties is the diffraction interferences. If it is a ray like a particles appear throwing means interference not possible, diffraction also not possible. So here in this case what happens is light rays bend along the surface of the obstacle and then come like this. Due to a reason, the shadow size is less than that of the object size or obstacle size. If the distance of the screen is still farther, the shadow may not be there also. If the light rays coming here, they come here like this and also like this, and in this region the light rays coming here, this light is coming here. So this area will be, light will be there. Shadow is only up to this portion. Beyond that shadow is not there. Due to that reason, aeroplane or birds flying close to the ground. Close to the ground, if they are very close to the ground from the sunlight, here shadow is forming. You can notice the shadow on the ground. But when they go little high, more height or some height, whatever the light shadow is there, the shadow is coming like this, and this portion is a shadow, and light coming from here bends along the obstacle like this and also like this. In this region again light is there. This whole light is falling here, whole light is falling here. That means shadow is only up to this. After that there is no shadow. So objects at higher altitude do not cast shadow on the ground because of the property called as a diffraction of the light. The light bends around the surface of the obstacle. Similarly, if you take a slit, one screen and slit, or cardboard you take and cut it, or hole you take, circular hole you can take also. The light coming from here, parallel rays I am taking for simplicity. The light everywhere is there, so light should fall here. Up to whatever the slit width is there, same amount of light should fall on the screen. But what happens here in the screen is, this should be the light portion. Some light will be there on even on the side outside of this slit length. That means some light will bend this side, some light will bend here also. This is a bending of the light. Here also bending of the light. So this light bending, it's at the side of the obstacle are deviated to the sideways near the surface of the obstacle is called as a diffraction. And here this light, this is supposed to be more brightness. But here completely darkness will be there. Here also completely darkness will be there. So some light is bending into the dark region, supposed to be dark regions, that also some light is there. This is called as an encroached light. Encroached, it means occupied inside other areas. Encroached light. Light encroaches the shadow region. Here also light encroaches to the shadow region. Some part of the shadow becomes equal to less dark. This is a complete darkness of shadow. Here less darkness of shadow. The shadow size is different from the obstacle size. That is due to the diffraction. Due to this diffraction also, the light waves after diffraction means here the waves bending and they interfere. After that you will get the fringes. The fringes formed is because the diffraction fringes is called as we have the multiple fringes slits also, single slit also. In the interference what we discussed. In the interference pattern, two slits, two slits we have discussed is easy cases. In these cases, the light fringes are formed not only up to these slits. Fringes are formed even outside the slits also. How the fringes are formed outside slit is because light rays are bending like to sideways. From the slits, light rays will bend to the sideways. That means this point P outside the slits length you have to take it up. That is because the bending of the light rays here, fringes are formed outside the slit portion also, and they interfere. That means along the interference we have the diffraction also. Interference and diffraction always exist together, and no interfraction and no interference do not exist. Next is the light is encroaching here and the fringes are formed here in these portions. Here more brightness means fringes will not be seen well. So fringe width if the beta is equal to lambda d by d. If the d is very large, if you have taken the slit, Young's lambda segment taken as very small slit, and fringe width beta is equals to lambda d by d. If d is very large, fringe width decreases so that you will not see the fringes only. You will not notice that. So more brightness we don't prefer here, and also we don't prefer more d. And more slit width also we should not take to avoid the spreading of the light by large amount. You will not notice the fringes. For that purpose, the condition required for the Young's double experimental fringe interference is d should be very small, so that the fringes can be wide and can be clearly seen. But diffraction pattern, daily life we can easily notice the diffraction pattern, like shadows disappearing, and even if you see the early morning hours near the mountains, before the actual sunrise, you will see some light spreading on the hill areas, surfaces. That is because light is spreading here, all brightness comes before sunrise itself. That is because of the diffraction of the light bending on the surfaces. Another is silver lining of the clouds. When the dark clouds you are taken, more white water is there in the clouds means that will become more darkness. The darkness of the clouds will, if the sun is behind it, light cannot be seen here, but some light will be visible at the corners, appearing more bright, shading like a silver. This is called as a silver lining of the clouds. That is because of the bending of the light at the edges of this dark clouds, that is due to diffraction. And diffraction fringes, the peacock feathers and spider web, and also collecting some water molecules, or even the surface that metal itself, and even the moths, some moths wings like butterfly wings, the colors falling on them will diffract, and DVD CDs, in that also some small grooves cutting will be there, and this DVDs small cutting of the grooves will be there with the help of the lasers. Light will be diffracted on the surfaces and you will see the colors. The white light splitting into colors due to the diffraction pattern here. Spider web is the colors is because of the diffraction pattern, and soap bubble colors are due to interference pattern. If you see with the half closed eyes through the eyelashes, you can see the fringes, and between the two fingers gaps, if you see through this gap, in this gap, if you see clear, keeping close to your eye, you can see the fingers in between the fingers. Small narrow gap, if you see, you can see the lines like this. They are nothing but due to the diffraction pattern. Even if the light comes from the cracks of the doors, sides, that also you can see the diffraction pattern in that. Next, the diffraction of the light. Single incident diffraction we have, and normal incident light. In this diffraction, there are the two types of the main diffraction analyzed by the two scientists. One is called as a Fraunhofer diffraction, another is called as Fresnel diffractions. Fresnel diffraction is not in your syllabus, so Fraunhofer only take it up. Whether Fresnel, Fraunhofer, final result is same. Final formulas are so same only. Only near the slit the analysis is different, and a way of analyzing is different. But final result is same in both the cases, so don't bother about that. What type of diffraction we are taking, but we are going to use Fraunhofer diffraction. In the case of Fraunhofer diffraction, light rays coming are parallel rays. So wavefronts are near the slits, just before the slit and outside the slit. Left and right, so the slits are at the slit. Only you are considering here, light rays should be parallel, and wavefronts will be plane wavefronts. It is more easy to analyze. Whereas the Fresnel diffraction of wavefronts are spherical or plane wavefronts. Parallel rays are coming. Parallel rays means what? Light rays coming from infinite distance. Whereas the diverging rays are there means what? Source is near to the slit here. So source is near means we cannot take the plane wavefronts. But practically we don't have the source at infinite. We cannot take the starlight for this experiment purposes. So what we take is a line light wave only we use here, and we take this light rays, diverging rays, and we keep one lens here. When we keep the lens near the source at the distance equal to focal length, light rays becomes parallel. Through the slit, light rays should be parallel, and light rays are again focused onto the screen with the help of one more convergent lens of the focal length equal to f. Focal length may be same, may not be same, doesn't matter. Left side of the slit is not important for us, right side of the slit is only important. The distance of the screen whatever taken is taken as equals to capital D formula, whatever taken may be given in terms of the focal length of the lens. Lens is kept very close to the slit. So through the slit, light rays are parallel means plane wave fronts we have to take. Plane wave fronts, and afterwards the light waves will interfere here, and after interference the fringes are formed on the screen. Now they are called as the diffraction fringes. Compared to the interference fringes, the diffraction fringes are not having the equal intensity. In the interference fringes, all are having the maximum intensity same. Dark fringes completely darker, when the two slits are having the identical intensities or same slit widths. But in the case of diffraction, the central fringe width is very wide and very brighter compared to other fringes. Alternately dark and bright fringes are formed, but central fringe is very wide, that is this value, intensity is maximum. Thereafter intensity suddenly decreases to 22% than that of the maximum values, and then 16% still less will be reduced. Percentage that is not important, and formula is not important. Diffraction analysis is very difficult actually compared to that of interference analysis. So I am going to discuss only the outside point required for the numericals. Here that maximum intensity has a maximum width, other fringes have the width goes on decreasing. This is called a central maxima, and then first dark means called minima, it is called the first secondary minima, first secondary maxima, second secondary minima, second secondary maxima. Like that they will use the word secondary. Don't bother about the terminology, just know that first dark, second dark, third dark. Secondary word, leave it. First, second, like the term only you have to consider. Next is we don't have the formula to calculate the central maxima here. What we have, the first dark maxima. So between the two darks we have the central maxima. The distance from the center to the top one is nothing but equal to y distance. It is y on the top, y at the bottom. So if you take the two sides, we have to consider this is y, this is y. So central fringe width becomes equal to 2y. Then formula for this fringes, this is just opposite to that of the interference formulas we have to take. For the diffraction formula, opposite of the interference formula for maxima and minima. For the interference, maxima condition is delta is equal to n lambda, but we take this as a minima condition, means for the dark fringes. Delta x equal to n lambda, phi is equals to relation between the phi and path difference is phi equal to 2 pi by lambda into path difference is the relation between the phase difference and path difference. N is equals to 1 to 3. Don't take 0. 0 we are taken for the interference pattern for the central fringe, but that is different. All are having the same, so we are taken there. But here it's not the same condition. For central fringe, we don't have the formula. We take a first dark, between the first darks only we take the central fringes. Next is, that means n equal to 1, you will get the distance of the first dark. Next is for the minima. Minima condition is delta x equal to 2n plus 1 into lambda by 2. N should not take 0, you have to take it as n equal to 1 to 3 onwards only. And here also, there we have taken 2n minus 1 and n equal to 1 to 3. But here we have to take only 2n plus 1 and to lambda by 2, and n is equals to 1 to 3 only. We have to take n equal to 1, you have to get here is 3 lambda by 2 onwards starts. Next is path difference is also equal to, we have taken as a d sin theta. Here slit width is taken as a, small a. There also slit width is a. Distance between two slits is d for the interference pattern by Young's double slit experiment. Here is a related as a d. So path difference equal to a sin theta is equals to n lambda. Wherever sin theta is there, we can replace this as with tan theta. That means tan theta is equals to y by d. This becomes equal to y by d into a into y by d is equals to n lambda. Also we can take from this, we will get the expression for y. So y becomes equal to the distance of the any fringe from the center. Y is equals to n lambda, n into lambda d by a is the formula for the y. For the first dark, this is for dark fringes, minima conditions. First dark means what we take is n equal to 1. So lambda d by a you will get. Lambda d by d for the interference pattern. This is y equal to lambda d by d up this part. Again bottom also required. So between these two darks, the central fringe width is there. So the central fringe width becomes equal to y plus y is 2y. 2 lambda d by a is a formula, that is the central fringe width formula. Mostly they will ask problems related to this point, this only, central fringe width only. So concentrate on that. Even theory exam also they will ask related to this. Next, these are minima conditions we already discussed. After that, we discuss term called as a resolving limit of microscope and telescopes. Resolution, magnification. Magnification means making the object appear bigger is called as a magnification, and resolving means making it clear. If you want to see it clearly, any object, how do we see the object? Any object, if you want to see, the light should fall on the object and reflects back and forms the image on the retina, which is inverted image, actually diminished inverted image, and that image only our brain senses as a erected image afterwards. So whatever you are seeing the object, light should fall on it and reflect it backwards. Whatever light reflected, that only we are seeing it. If blue light you are seeing means what? This is absorbing all colors except blue. White you are seeing means what? Is reflecting all the 7 colors from the white light falling on it. This one absorbs all the colors except blue. If appearing black, if the object appears black means what? It is absorbing all the fall colors fall on it. But perfect black body does not exist. If the perfect black means you cannot see that object or surface only. If you are able to see the surface means not perfect black body. Maximum wavelengths are absorbed, only little light is coming backwards. Generally dark blue, dark red, dark colors, they appear as black colors for us. Dark brown, that is appears as black. There is no black actually. White color do not exist, black color do not exist. White color is a combination of 7 colors with GR, or basic 3 colors RGB, red, green and blue. It appears as a white. No color means what? We call as a black. So here for the microscope is used to see the small objects appear as bigger. If you take the microbes, some small insect surfaces or bacteria, virus, the size of this object or 2 points of that object is what called delta x we take, and this delta x light rays coming from it as a lens going to the lens of this microscope in the conical form we are taking. The semi-conical angle is theta, and the medium, this is the air we are taken in the diagram. You can keep this object in the oil or any other liquids you are taken means that is called a refractive index equal to n we have to take, or mu can be taken symbol for refractive index. This n sin theta is called as a numerical aperture. N sin theta is called as a numerical aperture. Aperture is word is used for the place through which the light is able to pass. The opening through which light is able to pass is called as a numerical aperture. Numerical means only number, not having any units. N is a refractive index, sin theta, n into sin theta is called as a numerical aperture. And what is the resolving limit of this microscope is delta x equal to 1.22 lambda by 2n sin theta. N sin theta is a numerical aperture. This can be approximately taken as lambda by 2n sin theta. 1.22 is approximately as theta, lambda only. Generally, when the light is emitted from this object, 1.22 is preferred, that is obtained by integrations. If not emitting light, reflecting light you are taking means just lambda you can take, but approximately the same relationship. Next is resolving power. Resolving power and resolving limit. What are these terms actually indicates is appearing as more clear. More clear in the sense this limit of resolution indicates that less is the value of the delta x, more clearly able to see that object separated, well magnified, well separated, more clear. Means less is the limit of resolution, more clear is that means we say more resolving power. Resolving power is inversely related to the limit of resolution. That means just reverse of this you have to take. This is 2n sin theta by lambda. 2n sin theta by lambda. Mostly will be asked is resolving power comparisons with lambda, or how to increase the resolving power they may ask you. In this case, maximum value of the sin theta is equals to 1. When these were kept very close to the lens, on the lens surface only theta becomes equal to 90 degrees, then sin 90 is equals to 1. That is the maximum values. And if to increase the n value, what is done is generally the object is kept in the oils. Oils have the high refractive index. Transparent oils of high refractive index is preferred. Then n increases. When n increases, resolving power increases. Means more clear images we can see. And less lambda. If lambda wavelength is decreased, but white light we are using means average wavelength you have to take it of the 7 colors equal to approximately 500 nanometers or 550 nanometers. But if you are using the specific light, particular light only, monochromatic light you are using means lambda is less, means resolving power is more. Ultraviolet is also preferred, which we cannot see it, of course, with the help of the computers and the fluorescent detectors we can see indirectly the UV light. So UV light is made to fall on the object and reflected light is observed with the help of more lambda. Lambda UV is less, very less. Ultraviolet lambda is very less, so resolving power is more clearly you can see the object. Next is oil immersion microscope, means the object is kept inside the oil of high refractive index. Generally cedar oil is preferred. Cedar is the name of the plant type. This cedar oil is preferred to increase having the high refractive index value. Next is electron microscope. Electrons have the dual nature with when the speed is increased by large amount by accelerating voltages, the wavelength decreases. The electrons travels like a particle. It has a particle nature and also wave nature. and lambda is the wavelength that particle traveling like a wave. So effective wave distance traveled, wavelength, the length of the wave is nothing but equal to wavelength we call. It is inversely related to the accelerating voltages. They will give you as a voltage V only, but I am giving it as a V naught to avoid confusion with the velocity symbols. This is a V is the voltage or accelerating potential difference we call. More potential difference, less lambda, more resolving power. So resolving power symbol may be given as R, or I am giving it as RP also. R resolving power is directly proportional to V naught, inversely proportional to lambda. Okay, this they will ask the comparisons ratios. These are called as optical microscopes, means light we are using it. Optics is related to the vision, light is visible. Whereas the electron microscope means electron microscope is not visible to us. So dual nature of the electron is preferred here, and electron microscope has a very high resolving power compared to that of optical microscope. So even microscopes can be seen more clearly or more clear image, but the thing is that they have to be killed if you want to use the microscope with the electrons, because electrons itself moving means current only. Even if they are alive also, they will be killed by these electrons striking. Next, what is this actually? Okay, this after telescope I will discuss. So what is this actual resolving power means, where it comes from. This telescope, for the telescope compared with the eye also same principles used for the telescope. Eye means human eye or animal eye also. The telescope has two lenses, object lens and eyepieces. Near the eye, whatever the lens is kept is called as eyepiece. Same thing for the microscope also. This is for the microscope, eyepiece, object lens will be there. Here object lens has a diameter opening through which light can pass, that is called as the aperture width. Or diameter of the lens it's called, are also called as the aperture. D is not mentioned here. D is aperture of convex lens are called as the objective lens. Objective lens. Resolving power equal to 1 by delta theta, reverse of it is equals to D by 1.22 lambda. Resolving power directly proportional to D, inversely proportional to lambda. This point is only actually important for us. For this two distant objects, if we are seeing two stars for example, they appear very close to each other, but if you see with the telescope, microscope is used to see the small object as bigger, telescope means telling long distances, remote areas. So telescope is used to see the distant objects as a bigger and clearer images. When you see through this telescope, they appear very close to us and also bigger in size. So this telescope, the light rays coming from the two distant objects are meeting at this object lens, making angle theta bit at the lens. This delta theta or small angles means delta theta, we use the term, that itself is called as a limit of resolution. This is nothing but equal to resolving limit or limit of resolution. Resolving limit, delta theta. The formula for this is 1.22 lambda by capital D. D is the aperture width. Then delta theta is also equal to the distance between the two objects points by the distance between from the object to the telescope, that is equals to y by x. X is equals to distance of the object from the telescope and y is the distance between the two points, two objects A and B. T is the aperture of the objective lens. And the resolving power is what? A reciprocal of the resolving limit is called as a resolving limit. Reciprocal of the resolving limit is called as a resolving power. It is nothing but equal to 1 by delta theta. That is nothing but equal to reverse of it is D by 1.22 lambda. So how can you increase the resolving power? More clarity is by increasing the aperture width. D can increase or lambda decreased. But if you are seeing the natural light, we cannot decrease the lambda. So to see the particular stars or suns in the different magnification, then they use the filters. Filters are the transparent colored plates kept in front of the object lens. If you keep the particular color, that filters the other colors. Like that, you can filter the particular wavelengths and you can see the only particular specific wavelengths whatever you want. Other colors are filtered. Then you will see the different resolving powers or resolving limits. More clear means more resolving power you have to see. If you see the moon with the telescope, bigger it appears, but it should be clear means what? Every point on the moon should be appeared clear means you must have the high resolving power. That is the reason why these professionals use the cameras with the high bigger lens size. More light is collected means more light rays, each light ray carries the image of the object from it is reflected. More light rays come means what? More image information is collected by the lens. Therefore, more aperture if you have taken, more light comes. And more clear we can see. So for that purpose they will ask you generally is how to improve the resolving power is by increasing the aperture size or diameter or the size of the objective lens or decrease the lambda. Practically we cannot change the lambda except for the filters, but otherwise lambda is you have to use the white light average value 500 nanometers or 5000 angstroms. For human eye, what is the resolving limit? Human eye resolving limit is 1 minute or 60 seconds. That means if you see any person's shirt having the lines, if the person is wearing the shirt having the lines, vertical lines or horizontal, whatever it is. If the white, in between white, say for example blue lights are there. If you see from the distance, you don't see these lines gapping between them. They appear as a single color line, colored only. If you see from the distance, it appears as the colors, you don't notice the gap between the lines. But as you come closer and closer, you can see the lines as separation. More clearly you can see them when they are at particular distance onwards. As you go away, you cannot notice the gap. So here, as you going towards the nearer, delta theta increases. Going away, delta theta decreases. Less is the delta, still you are able to see clear means more resolving power. Less the limit of resolution, more resolving power. Units of the resolving power is 1 by radians. Limit here is delta, angle is radians or degrees. You have to take SI unit is radians. Here resolving limit is meters. Here is per meters resolving power. And for this case, what happens in the eye actually, why we cannot see them clearly is, when you can see them clearly is when the light rays coming from the 2 points on the shirt meeting near the lens of the eye, making angle is equals to 1 minute. This is angle's place, or 60 seconds. This is equals to 1 minute. 1 minute equal to how much is? 1 minute is equals to 1 by 60 of a degree. 1 by 60 of a degree, that light makes small angle near the eye, then we can see them that there are 2 different points. Otherwise they appear as a single point only. That is called the limit of resolution of the human eye. Eagles have the more resolving power than the humans. And what happens in the eye actually? Each light coming from the each one forms a diffraction pattern like this. Maxima, first minima, maxima, minima. Maxima, minima intensity goes on decreasing. Don't bother about the higher numbers. We take only maxima and first minima on both sides. So we see every point. If you take this point A, this point B, the light ray coming from these points in the eye, they forms the maxima and minima. Maxima and minimas. What about the second one? The light, this point A light. The B light also forms the maxima minima. If that is very close to each other, means they are not forming far away. If you are taking, means angle is less. The light rays coming from this A and B are very less. So we take a maxima minima like this. This is very less. So they combined, what you see is this one. But if you go away, then what happens here is this is the maxima. And here also the first maxima should fall on minima of the second ones. Maxima of the first one falls on the minimum of the second one. Then you will notice some difference between these two. This is what we see. This dotted line is what we see in the eyes, A and B. So you are finding some gap here. This is the resultant motion. So that means when you see that minimum condition, just separated, when you want to see the 2 distant objects are just separated, 2 stars just separated, 2 lines just separated, one microbe is their ant, at some distance it appears like a dot. As you come closer you can see the legs, etc. other points. When you see that just separated points means the one maxima, each point from the diffraction point of the retina of our eye. So the maxima of the first point, first object light should be on the minimum of the second object light. So this maxima is on the minimum of this one. One maximum of one falls on the minimum of other. Then you will see just separated. Well separated means what? They are much separated formally. This is a maxima minima, maxima minima. So you will notice easily the much separation between the objects. But every point, every light ray coming from the object forms a diffraction pattern on the retina. Even if you take the torchlight and focus onto the wall, you will see the one ring. That light, because of the source is circular aperture, light falls, more brightness here, and you will find just a dark ring, and again brightness, again dark ring. As you go away, the darkness increases, the brightness decreases, because the fringe width goes on decreasing. Here we are taking the slit, so fringe we are taking. Here we are taking the circular ones, you will see the circular fringes. Circular rings, like we will notice, is more bright, small dark fringe, and again bright, light brightness. Brightness goes on decreasing, darkness goes on increasing. We need to work out the problems from this text, from the material based on this diffraction pattern. Problems are very few problems are important. One is central fringe is maximum asked is related to central fringe, and the telescope problems were repeatedly asked. And one more thing is light and sound diffraction. You will notice more diffraction of the sound than that of the light. Means if somebody is talking behind the building, if the sound bends and comes towards you, because the sound has longer wavelength compared to the light. Light has